So today we're going to learn about this button on your calculator. Anybody ever wonder about this one? Try to find that button, the e to the x key. Do you see it? Okay, this is called, this is pronounced Euler. That's how you pronounce this dude's last name. Euler is what you would say. Okay, this is the Euler number. And it's named after a guy, Leonhard Euler, who was the one that discovered it. Okay, it's much like the number pi. It is irrational. It goes on and on and on and on forever. It does not have a, it doesn't have an ending value. It doesn't have a fraction that we can use to describe it. It does have a numerical, like how pi has 3.14. Euler number, the E number, has a value that's approximately 2.71. Okay, so it's approximately 2.71. So if you take out your calculator and you do e to the 1 power, so you hit the e to the x key and then select 1 and just take it to the first power, you should get 2.71, blah, 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 right? Everybody see that? All right. And so maybe after the SATs are over, when we have a little bit more time, one of those flexible days, we can go through the actual activity that can help us to describe kind of the process that Euler went through when he discovered this number, this wonderful constant, kind of what, whenever Pythagoras discovered pi. We can kind of describe that to you, but it does take a while, and you guys know we're short on time. So I promise you we will get to that, but it's just the growth pattern, right? If we take 2.71 and raise it to the power of x, will it be a growth or a decay? If we're raising 2.71 to the x power, is that a growth or a decay? Come on, go back to what we've been talking about all week. Isn't that the value of b? Isn't that bigger than 1? So it is. It's growth. It's a growth pattern. So it's nothing like magical or anything. So when you see e to the x, there's no need to panic. It just means that when you put a 0 in for x, wouldn't you still get 1 if we graphed it, right? And if you put a 1 in for x, we've already done that, you get about 2.71. So somewhere around here. So it would still be the same type of positive growth pattern that we've looked at before. You still have a asymptote. That's the x-axis. All the other rules apply. It just means that our base b will always be the same number, which is the number e, approximately 2.71. So e is one of those numbers that shows up a lot in the real world. It's going to show up a lot in science. It does show up in banking. When we talk about compound interest, we'll talk about, that's probably the one that we're going to use the most in here, is the banking situation. Okay, so that's the one we're going to kind of just jump on into. What would I do? What type of an exponent would make this type of function be, instead of a growth function, be a decay? What if I wanted that graph, instead of it being a growth function, what if I wanted that to be a decay function? I would need the inverse, wouldn't I? So what type of, I can't change my base, right? I can't make e become anything other than 2.71. E is always going to be 2.71. So it's not like I can make my b value become a number between 0 and 1, because that's what it means to be decay, right? So what would I do if I wanted that to be a decay? A negative exponent. Ah. Because what do negative exponents do? Doesn't it flip your base, doesn't it? It makes it be a reciprocal. So everybody take out your calculator for me and do 1 divided by 2.71. It's just an approximation here. We know that, right? 1 divided by 2.71. Do you get a number between 0 and 1? Ah. So there's your decay function. So then you have something that looks like this. So when you're dealing with these types of functions, when you have the Euler number, you do have to look at what is the exponent, right? If it's raised to a positive x, then it's growth. Negative exponent, it's decay. We good there? All right, so make sure that you write that in your notes somewhere, the difference. Because the other ones that we've done, we look at the value of b to decide growth or decay. But now we have to look at the exponent because our b value is always going to be e, the Euler number, 2.71. We won't be graphing a whole bunch with these. The graphs are very similar to what you've already done, right? There's no magic to it. It's just the b value is going to be that same number, 2.71. So if you want to put 2.71 in place of e because you like numbers better than this letter, that's fine. Just like you can use 3.14 to approximate the value of pi. Nothing at all wrong with that. But how do we actually use it? That's probably the more important part. So, compound interest. Compound interest, right? The more you compound, the more money you make. And banks figured that out. They're like, okay, if we only compound once a year, you know, we only get our money once a year. But if we compound twice a year, not only do we get our money more often, but we actually earn a little bit more. And if we got it quarterly, got it 4 times a year, we end up at the end of the year even with more money. So let's just do an example real quick. We'll use simple numbers. Let's see how much money you get at the end of the year if we have a $10,000 investment at, let's say, a 5% interest. And we're going to compare between getting, we're going to compound quarterly, right? So 4 times. And we're going to have that investment in there for 10 years. And we're going to compare that to the amount of money that we get at the end compounding it monthly. Let's see what the difference is of our investment compounding quarterly or compounding monthly. So if some of you would do the quarterly and some of you can do it monthly, that would be helpful. And let's see the difference in that amount. So once you have a number, let us know. All right, so here are the results. Compounded quarterly, you get $16,436. Compounded monthly, you end up with $16,470. And you're thinking, that's not a real big difference. You know, what, $34 difference over the course of 10 years? That's not really a big deal. But to a bank, that's a real big deal. Because it's not just your loan or your investment, right? You're talking about possibly millions of customers. And so they're like, well, I wonder, what if we compound it more often than even monthly? You know, what if we did this every day? Right? What if we compounded this every day? And so they were like, okay, well, let's do this every day. So they did 1 plus 0.05, compounding at 365 days a year for 10 years. That means they collect the interest for that one day, and they add it back into the principal. And so the next day, your principal is not 10,000, it's 10,000 plus whatever interest you earned the previous day. So now you're earning interest on top of your interest. And then every day, or every time they compound it, they're adding that interest back into your principal. So that's why it's like you ever hear of someone saying they're compounding your problems? Like you're making problems on top of your problems on top of your problems? Same thing here. You're adding interest on top of interest on top of interest, which is a good thing. We like compound interest. It helps your money to grow a lot faster. And for a bank, if you're getting a loan from a bank, they want to compound this interest as much as possible. Right? They want to compound your loan as many times as they can, right? Because they're going to squeeze every little penny out of you that they can. All right, who has this number? 16,486 with some change. So now they're like, hey, we even got some more money out of them. I wonder if we could even compound this more often, right? Like every second, right? And so they started playing with this, and they were like, let's do this more and more and more. And at some point, you kind of reach you reach a point where you're not going to get any more money out. It's like you hit that maximum level. So as the end value keeps increasing, you end up not really adding very much more money to that total. So let's just jump it. Let's jump up to like 1,000. Let's put n is equal to 1,000. Let's see what we get there. So $10,000, 1 plus 0.05. Now we have 1,000 in here, raised to the 1,000 times 10 power. It seems like that would jump up a whole lot, right? Jumping from 365 to 1,000.
If we would have asked for the difference, we would have just subtracted this from that, and that would have been the answer.
Hold on just a second. So the difference between compounding every day, 365 times a year, and 1,000 times a year is a difference of only $1. So you see how you start reaching that limit, right? That asymptote, right? You're getting closer and closer to, like, okay, well, I know it's just $1 more, but it's $1. And if you have 1 million customers, that's $1 million, right? So the greedy bankers were like, well, how much more can we get? And so this whole idea of this Euler number, this is kind of how it was developed, or there's definitely an application to it. So there is a formula we're going to be using that's called a continuously compounded formula. Continuously compounding interest. It just keeps going. It keeps happening like every instant. So the end value like reaches infinity, right? Because it's just constantly happening. And that formula is this. To get the ending value that you want, you take your initial investment and you multiply it times the Euler number raised to the power of R times T, your rate times T, your number of years. So we don't have an n value anymore because n is, it's too big, right? Because we're saying it's happening constantly, never ever stops. Like you can't put infinity in for n, right? So that's where the Euler number comes in. So some people call it the PERT formula because it spells out the word PERT. So principal, right, times e to the RT power. So let's see that last example that we did. If it's compounded continuously, let's see what we would get. $10,000 compounded continuously, 5% for 10 years. Now again, you want to make sure that your rate times time, you go ahead and multiply that first before you raise it to the power. So that's going to be to the 0.5 power, 0.05 times 10, right? In this, please make sure that you do e to the 0.5 power first, and then multiply by 10,000 last. We should get somewhere around 16,000, somewhere around the numbers we were getting before. What'd you get? Same one?
With more change.
16,487 with a little bit more change. Yep. This is the absolute maximum amount of money that you could squeeze out of that investment. And that'll be the application that we use for the Euler number today. Okay. There's going to be other applications that we see of it, especially as we get into logarithms next week. All right. Assignment.